Just to remind you guys, I am in the room half an hour before class starts, and I'm in the Math Study Center many times. And if neither of those work, then you could always send me times you're available, because I am in my office more than I say I am, because I got shit to do. But if you're like, I could make it this time, I could pick one that works for me too, right? In case any of my available times doesn't work, you just gotta reach out to me and say, hey, can you meet this time, this time, this time? I'm like, the third one, right? Okay. All right, the exciting part of the class is here. As I adjust my video camera. Here we go. All right, so if there are no other questions from homework, I'm going to do this one. But is there anything else? A few more people came in. All right, so let's look at 11.6. It says this. 2/3 plus 2/3 times, what was it? 5. Wait a minute, what does that say? Oh, 5 over 5, okay, neato. 5 over 5 plus 2/3 times 5 over 5 times 8 over 7, right? Yeah, okay. Plus dot. Now that is some trippy shit. What does that look like? Do you guys see how this is not a straightforward thing at all, right? If you're trying to figure out, well, here's n equals 1, here's n equals 2, here's n equals 3, right? It's not just 2 to the n or something. It's not just a single, every time there's one more element. What other function do we have that does something like that, where every time you increase it, it actually adds another piece? There's another function that is exactly that. Factorial, right? 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. So this is obviously, though, this can't be just n factorial, because is it going up by 1? No. So on the top, for example, it's going up by how much? 3. So let's play around with some stuff. So n factorial would go up by 1, right? So I do 1 times 2 times 3 times n minus 1 times n, right? Goes up by 1. So that doesn't work. If I just do something like this, does that make it go up by 2 or 3 or something? You guys see what I'm asking? Somehow this is some adjusted factorial. I'm just like, how the shit is this adjusted? So what would this look like? Well, this would just look like 1 times 2 times 3 times n plus 1. I mean, that doesn't do anything for me. What else could I try to do so that everyone is not equally spaced? Do you see how n plus or minus anything is they're still gonna be separated by 1, correct? So there must be some other.
You would add the n to the 1, or have an n with the 1?
N plus n? Well, let's try. What's n plus n?
2n.
2n. Let's see. What's 2n factorial? If n is 1,
It'd be just
2. If n is 2, 4. Okay, this is getting somewhere. Yes?
Yeah.
Okay, but it's supposed to start, it's supposed to go 2 to 5. Like on the bottom, it's separated by 2's, yes? All right. But it's supposed to start at 3. What can you do to this? You guys agree this is even numbers? And I need odd numbers. So what can I do? 2n, you can do it. Plus 1. All right, let's test it. N equals 1. What do you get?
3.
You get 6. You get 3 factorial, right? For n equals 1. For n equals 2, you get 5 factorial, right? Okay, so we're still not quite there yet, right? So this is just sort of playing around with some possibilities. Okay, maybe. So what else could you try to do? So these are odd numbers multiplied by the next odd number up. So what else could you try to do? I mean, just start playing around with some possibilities. Or, well, okay, we'll leave that one. I want to say what I was about to say, but what else could we do? Maybe this isn't a factorial. It just kind of looks like a factorial, right? So for n equals 1, it's 2/3. And then for n equals 2, it's 2/3 times 5/5. And then for n equals 3, so somehow it keeps multiplying by the next thing up. And the next thing up is up 3, up 2, right? Up 3 on the top, up 2 on the bottom. Okay, so any other ideas? No.
What about canceling, like the telescoping series? Is there a way to get a bunch of stuff to?
Oh, I see.
cancel out?
Not quite. I like the idea, but no. So let's take a look here. So I want 2 times 5 times 8. Isn't that 2 times 3 plus 2 times 3 plus 2 squared? Not 3 plus 2 squared. 3 plus 2 times, there it is, twice 3 plus 2. So it's like 0 times 3 plus 2, 1 times 3 plus 2, 2 times 3 plus 2, right? Okay, I like it. I need you to start to understand the playing around that you have to do. So we started with, okay, maybe it's some kind of factorial, and it might still be, I just have to play around with this more. So that's like looking at each piece. For like n equals 3, it's got to be this. No 3's plus 2, 1 3 plus 2, 2 3 plus 2, the multiple of all those. Now what does each one of these look like? Let's see. Like for n equals 1, this piece would be n minus 1 times 3 plus 2, right? So that's what each one of these looks like. Yes? Okay. So let's see. If I kind of, I don't want to say this. Yeah. So what does that actually look like then? That would be 3n minus 3 plus 2, 3n minus 1. Right? Now let me ask you this. This one, let's see. What if I took this expression, 3n minus 1, and I put an n plus 1 in? What does that become? 3n plus 2, right? Which kind of looks like that a little bit. Okay. So I'm just playing around here. I don't want to kind of give you the answer, but I want to show you what to kind of play around with. Let me see, what else could I say? But do you see what I'm doing? I'm trying to see what will construct this. And it almost has to be some kind of factorial to keep having another thing add on. How else can I say this? Something else you could think about, it doesn't necessarily have to be factorial. It could be like an nth power. So for example, this, 2/3 to the n. What would that look like? A few terms, right? What would a few terms of this look like? 2/3 plus 2/3 times 2/3, right? So do you see how this is kind of like possibly even an, not geometric, but it's sort of like somehow multiplying by a different multiple each time? So maybe instead of being a constant inside, maybe there's some dependence on n inside. Maybe? You see that? Okay. I'm trying to leave enough for you guys to play with, but I really want you to understand how to play with this. Right? And that's a difficult thing to get at, because As a teacher, if I come in with something too prepared and I just show you every step, you're going to come away from that feeling like, I'll know this when I can just do it, just without much, no, holy shit. And if I come in with like no thought, then you get the teacher that's like, I'll get back to you. You know, and if they're doing it every time, that gets annoying. But I've got to show you some just playing around. Like, I'm trying to be like, I don't know what to do. What am I going to try? I'm just going to try to capture this process. So think about this. What would it look like? Let's kind of play around with that a bit. What would it look like if it was 2n over 3 to the n? What would some elements be? N equals 1 would be 2 over 3. N equals 2 would be, yeah, so let's see what it would be. It would be 4/3 squared. So it would be like 2 times 2 cubed over 3, right? Squared, so over 3. Let me see if I can do this. 2/3 times 2 cubed over 3. Which is not what we want, but it's kind of getting in that direction. Okay, so the thing I was going to say earlier was you might want to see if there's any examples like this. But again, this is the sort of playing around with stuff that you have to do. How can I make a series that will end up with terms doing this kind of thing? And that's getting closer, right? Every time. So what would the next term be? 6 over 3 to the 3rd power, right? Which is, let me see if you guys get this. So it's 6 times 6 times 6 over 3 times 3 times 3, right? Stay with me. Jeff, write a 3. Which is 2 over 3 times, what do you got, Jeff? 2 cubed over 3 times blah, blah, blah. So you can try to pull this apart to see if you can't start seeing how to construct those parts. Okay, so this one is a nifty one for damn sure. But I'm almost certain, if I remember correctly, there's an example that's sort of like this. So always look at the examples first place if you're not sure how to do something. But I mean, this is the kind of playing around that you have to do. Let's do, let me see. Well, it's not much more I can do with that without just telling you. Okay. So that doesn't answer the question, but at least hopefully it starts to let you see this is the kind of playing around that I have to do. I know I left that a little bit, right? So if that's the only one you have trouble with, okay. But that one requires a lot of playing around to kind of capture what's happening. And let me see, I'm almost certain. Yeah, sort of like that. Yeah, they kind of do an example like that, but not really. Okay. See if I can, yeah, look at number 20, for example. Here, let's do number 20 together, and then I'll show you how that applies to this. Here we go. Okay. Because actually, you don't even need to be able to write it in like closed form. So let me show you. Wait, did I get the right thing up there? Yeah. To the end, and factorial over, and look at the bottom of that. That looks vaguely like what we're working with up top, right? So there are some factorial ideas that we can't write with the factorial. Let me, do you guys see how this is sort of like a factorial, and it's sort of like what we were talking about earlier, right? Why do I not need to be able to write this in closed form? Because what would an plus 1 be? You can do it. Top's easy, right? And forget about this because we're going to do the absolute value, so who cares about the negative 1 part? What's an plus 1?
So 2 to n plus 1.
2 to the n plus 1?
N plus 1 factorial.
N plus 1 factorial?
Over 3n plus 1.
No.
580 what?
5 times 8 times 11, 3n plus 2 times, because what's the idea here? Every time n goes up, I get one more piece. If n is 1, what's on the bottom? This starts at 5 and it goes up to 3n plus 2. Well, if n is 1, what's 3n plus 2? So it starts at 5 and it ends at 5. So the only thing on the bottom is 5, right? n equals 2. It starts at 5 and it goes up to 3 times 2 plus 2, which is 8. So the bottom will be 5 times 8. So for the nth term, it goes up to this. So for the n plus 1 term, it goes one more step past this. Okay. This is good because I didn't realize they didn't give you any examples like this already, so we'll do one. So it's a lot less freaky than what it seems at first because you can actually just leave the shit in here because what's going to happen when you do a ratio of these two? Do you see how a bunch of stuff's going to cancel? Yeah. Okay, I like it. You guys see that? So you can do a very similar thing with that number 18. Okay. I do want to show you, so real quick, I don't know if you guys want to finish this up, but if I did this, might as well finish this up. The ratio test says take this one. This is 3n plus 5, is that cool? Times, divided by this, so times the reciprocal. Shoot, I should always do this. Always show yourself. That one and the one next. Over 2 to the n factorial. So look what happens between these two. All that goes away. Very nice. So very similar thing's going to happen on number 18. And then, of course, between these two, I don't know if you guys are at the point where you can see that's just going to be 2. I lose n2, so I got 1, 2 left. And this one is going to be n plus 1.
1 plus 2?
Yeah, so on the top it'll be limit 2n plus 2 over 3n plus 5, which is 2/3. All right, ratio of the highest degree terms, 2/3. And what's important about 2/3? Less than 1, which means that the series is convergent. I love it. Kick ass.
So you multiply it by the reciprocal.
Yeah. Basically, almost every series we see has some kind of fractional element to it.
Yeah.
There's very few that are just in a straight line. We're going to see some tonight, but so I almost always am going to just multiply by the reciprocal. Yeah. I want to show you an interesting. So remind me, n factorial means what?
Like multiplying all the way up to n.
Yeah. So you can think of it. You can either think of it starting at n and going down to 1, or you can think about it starting at 1 and going up to n. Yeah, right. Either way, and sometimes one way or the other is going to be better in some series analysis that you're doing. So you have both methods available to you. So sometimes one's better, sometimes the other one's better. Now, as I'm talking, I'm like, good Lord, Jeff, do you remember this? There is like a double factorial where it steps by 2 instead. So it accomplishes sort of like what we're trying to do here. So it goes like n times n minus 2. Yeah, as they say that, I'm not sure. But there is a double factorial, which means there is a triple factorial. I don't know, I haven't looked that up in a while. I'm pretty sure that means, but it could be something. So I'll look up double factorial. It's not very often used, but anyway, that's not going to be a big part of our class. I just want to let you know there's beyond just a single exclamation. There's more. So this is just the more and more excited end. Okay. So is that cool? Do you guys see how this is going to help you out with number 18? Yeah? Okay. Okay. All right. Anything else from homework stuff? I mean, really, it's just the 11.6 that we've done since the test, so. Okay, so let's do this. Let's finish up this this worksheet I gave to you guys. Anybody need that? The one from 11.6? Oh, by the way, because I'm going to forget. Anybody not get their test back yet? No, okay. All right. So this sheet, we did the ratio test stuff at the top. Let's take a look at and basically what we just did was ratio test, but in case you weren't here last time, the truncated lecture about ratio test, and this is one of my favorite tests. And then, yes, anyway, we'll get past it. If I look at the limit given some series, if I look at the limit of the ratio of one term to the term before it, if it was geometric, what do you got, Jeff? You could do it, buddy. You're doing stuff. Good job, good job. There it is. Excellent. You could do it, my friend. There. Look at that. Ooh, look at that. Okay. Blah, 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 blah. Right? Is that geometric? How do you check to see if it's geometric?
Common ratio.
Yeah, common ratio. What do you mean? Be more specific when you say common ratio.
So like for that, it's like 5/7.
So you basically take 1 but divided by the one before it, right?
Yeah.
10/7 divided by 2 is 5/7, right? What's 50 49 divided by 10/7? 5/7, right? Do you see how to see what the common ratio is, the number I keep multiplying by, I would take one term divided by the one before it. Term divided by the one before it. So if I do ratio test for any geometric, the answer will obviously be just a number, right? In fact, can you guys real quick, what's the series form for this? Oh, shit. So the R is 5/7, correct? So I can just put that in there. And actually, if I want to be nice to myself, I could do this. Now, why is that being nice to myself? Because now when n is 1, that shit doesn't show up because it doesn't really show up here. And what's the first number? What's the first element? 2. So I keep putting commas in. I want to put this there. Let me stop for a minute. Is everybody with what just happened? It's the beautiful thing. If you make this piece 1 to begin with, then what goes here? The first number, right? So when n is 2, I get 5/7 times 2 is 10/7, and so forth. So let's try this with that. So an is that. 2 times 5/7 to the n minus 1. What was an plus 1?
2, 5/7, n?
Yeah, n plus 1 minus 1, n. Okay. I would never do ratio tests for a geometric, right? But there's a purpose, there's a reason I'm doing this. So if I do set this up, this limit's kind of silly because if I take this divided by this, and I like write it so humans can read it, the 2's cancel,
n's and 5 over 7.
So I have n up here, n minus 1 up here. So n minus 1 is 1, so this would just be 5/7. So the limit is kind of silly because it just becomes a number. Okay, now, so what I desperately try to do is, you guys know geometric really well because it's one of the first ones we did. And the idea is really silly simple. If I keep multiplying by something less than 1, that means I'm going to decrease fast enough so that the series actually converges. That idea is really straightforward. So ratio test says, okay, if I have a series that's not really geometric, but in the long term it sort of becomes geometric, like it sort of starts to look like it's multiplied by 2, divided by 3, or whatever, then that's basically like a geometric in the long term, and then if that limit comes out to be less than 1, it converges. Greater than 1, it diverges. What if it equals 1? Inconclusive, you got to do some other test. So I'll try to do an example that comes up inconclusive so we can see what the hell to do with that, right? Okay, so it's not just some amorphous possibility. Okay, so ratio test and root test are both built off the idea of geometric, which is why the result you interpret it by saying is the limit less than 1. Convergence, same as geometric test, right? Okay. So let's see, let's try, what if I wanted to apply, I'm going to take a silly one, but oh well, get out of there. What if I want to apply ratio test to something that really doesn't make sense to do it to, but let's do it anyway. Okay. This is kind of an extreme. If I said, does this converge, would you use ratio test? Can anyone tell me very quickly, will this converge?
No.
I got some dissension, I like it. So what's it trying to be?
Looks like a harmonic.
1 over n, looks like harmonic.
Yeah.
That's going to diverge, right? Okay, now, you got evil math teacher. I could give you this one and say, use ratio test on this, right? So let's try it. Here's an. Yeah, what's an plus 1 look like?
N plus 1 squared. N plus 1 cubed.
Right, just put a bunch of n plus 1s in. I like it. So then you would do the limit. So n goes to infinity of the next term. Times the reciprocal. Now, does anyone notice, what's the degree of the top? What would it be? What's the highest degree here?
Squared.
Squared. What's the highest degree there?
Cubed.
So what's the degree of the top? 5th power up top, right? What about the bottom? 5th. So what's the limit as n goes to infinity, same degree? The ratio of the coefficients. What would the coefficients be? 1 to 1. So this is 1. Remind me, what's it mean if I get 1? Inconclusive. So this is what I'm trying to show you. This is kind of an extreme example because from the beginning we're like, why would I do ratio test? But this shows you how the ratio test, there will be other things that you will get a 1, which means there was some simpler way to look at it. So in this case, the simpler way would be like a comparison test. Why would I do ratio test? I just do comparison test, right? You guys follow?
Yeah.
So when I get a 1, that does suck because I don't know the answer yet, but that means, oh, there's some simpler way to do it. There's some other way to look at this from the beginning. Okay. You guys semi with me?
Yeah.
So I wanted to show you a concrete example of when the ratio test fails. It couldn't tell me anything. Okay. And basically any rational expression, ratio of polynomials, will always have that same problem. There'll always be 1 because there's an easier way to look at the thing. Okay, I like it. I like it. Now, root test. root test is fantastic. But it doesn't happen very often. So what if I had yeah. So real quick, if I have this, do I need any, can I get the answer for this easily? Does that converge at average? Converges. What is the nth root of 2/7 to the nth? 2/7. And that, again, is just another actually more direct way to get what r is. If I take the nth root of a geometric, I get what r is, correct? So if I take the nth root of some general series and I get a number, that means in the long term it's acting geometric. It's exactly the same idea. It's just a much more direct. So the funny thing is, root test kicks ass because you will always know when to use it. When everything is being raised to an nth power, because then the nth root kills that. If I put an n here, no root test. Do you guys follow? Yeah. Nth root of n. It's exciting. Let's not do that. So the root test would say the nth root of absolute value is no freaking negative, so who cares? So of course what happens there? The nth root and the n power cancels. And what's the limit of 100 over n? It goes to infinity. 0. And that is definitely less than 1. So in the long term, if n is 18 trillion, which is apparently one of my favorite numbers, it's effectively multiplying by 0. Because 100 divided by 18 trillion, for most humans, is 0, right? You guys with me? If the probability that an asteroid is going to hit us is 100 out of 18 trillion, it's basically not going to hit us, I mean, right? And then, of course, it hits us, we're like, you suck, you math person. Psh. Okay, sorry. You guys kind of with me? Yeah. That's a little, it never equals 0, but it gets so stupid close to 0, it's basically multiplying by 0 in the long run. That's what that means. Okay, maybe. Okay, so I think I asked you last time how you felt about ratio tests, because we've done some ratio tests. Compared to some of the other tests we've done, how do you feel about ratio tests? It's a lot better. That's the way to feel about it. If right now you're like, they all equally suck, Jeff. Shit. Please come see me, right? If you're at the point where you kind of get what we're doing earlier, this should be pretty straightforward. And I don't mean to make you feel bad if it isn't. Just come see me if it isn't. Okay, all right. So let's try this sheet. Can you guys try, well, I basically just did number 1, correct? Yeah. Well, I forgot. Oh, well. Can you do number 2 for me real quick? That's basically number 1 with the 10 up here. Let's do number 2. By the way, if there was a -1 to the n or whatever in there, we're doing the absolute value. So in fact, I really should just make that apart because that's going to become huge. You're going to want to get used to having those absolute values in there. So any -1 dependence just kind of goes away when we take an absolute value. Right? So you get the limit as n goes to infinity of And then how do you evaluate that? Yeah, let's really just go whole hog into hospital guy. Do that shit too. All right. So then they get 1 over n over 1, which is 0, which is
Convergence.
And let me say more specifically, what kind of convergence?
Absolute.
Absolute convergence. Kick ass. Now, if they gave you one that doesn't converge absolutely, I could still ask you, okay, does it converge conditionally? And then what would you do? Yeah, AST, right? Do the AST. The AST. Okay. You guys, how do you guys feel about that? So, ratio test is directly seeing what I'm multiplying by. So if I divide a number by another number, I see what multiple that is of the one before, right? That's what I do. So it's really, it's getting R, what R seems to be directly. The root test is actually kind of more direct. It's just like, if you keep multiplying the same thing, just take the nth root and you can see what that thing is. So none of these, nothing on here, on the root test. Well, look at number 2 under the ratio test. Is that geometric?
Yeah.
Yes, right? Isn't that 8 to the n over 7 to the n? Isn't that 8 sevenths to the n? So couldn't you just have said it's geometric, 8 sevenths, greater than 1 diverges? Yes? Okay, but every other thing on here, 1, 3, and then 1, 2 down there, none of them were geometric, but by applying the test we're seeing in the long run, does it start to look as if it's geometric? And then whatever that multiplier is it less than 1, just like a geometric? Okay, I think I've hammered that home. All right, okay. Okay, so what I want to do, let's do this. So 11.7, I kind of prepped you guys for 11.7. 11.7 is just like that section in chapter 7 that was like all the integral methods all at once, right? So that's what 11.7 is. So if you thought you're done with integral tests and all that because we just did the test, you're not. It's all in 11.7. I love it. Let's try a few problems out from 11.7. Just going to pick some at random. That should be exciting. That's a little bit on the nose. My God, do I have to bring my freaking glasses? Jesus. Okay, there it is. Yeah, what do you guys think about this? Let's see. All right, so let's talk about some general things to look for. Could this be conditionally convergent? Could it be? I'm not asking is it, just saying could it be?
Yeah.
Yes, right, because it has an alternating part, it could be conditional. Do you check conditional convergence first? No. Okay, good. So here's one general kind of thing. Even if it's got a alternating piece to it, you don't start with conditional convergence. You don't start doing the alternating series. That's why. Can anybody tell me why I say that? Remember, I'm evil. I could just be misleading you. It's what I'm saying makes sense. Why would you not start with that first? If it's absolutely convergent, then it automatically is conditionally. If you leave all the terms positive and that converges, then making every other one negative is definitely going to converge. You guys see what I'm saying? This is why I said earlier, always test absolute first, because if that's true, you're done. If you do conditional first and it's true, you're like, oh shit, now I got to do absolute also. Might as well, try absolute first. Maybe you're done. So let's try absolute convergence first. So let's look at this guy. All right? Let's try absolute first. So does anyone have any feel for what this might do? Why do you say that?
Because I saw it on the test and it also converged. It was kind of similar, but it was linear.
Oh, I see what you mean. Yeah, it was linear on the
Just like
top.
thinking about that, yeah.
But in terms of rate of increase, which one of these is increasing faster?
Bottom.
The bottom by like how
By a
much?
lot.
By a lot, right? Okay. I don't know if you guys remember what we did. What was the problem? It was like, it was just n over 3 to the n or something?
It was like
I
that.
think it was, yeah. Don't put a limit, Joe. Okay. Right? And I don't know if you guys remember what I did. I said, shit, man, if only that top was like 2 to the n. Right?
Right.
Then this would be easy. So I feel like this converges for the exact same reason you just said. Is everybody with me so far? I feel pretty good that converges, which means do I want to find a ceiling or a floor? If I want to do, so I could do a ceiling, right? So I want something that's bigger than this. So is 2 to the n bigger than this after some, for what value of n? Is 2 to the n bigger than this for 1?
Yeah.
Shit, yeah, and then forever after that, right?
Yeah.
All right, so let's try the same thing here. And then we'll see if you want to try something else, right? In fact, let me just say this. Before I even do all that shit, does anybody want to try, like, ratio test? Can I use root test? Why can't I use root test? Or why do I definitely not want to?
Numerate.
Because it's not all to the nth power,
Yeah.
right? Nth root of n to the fourth is a little weird. It's doable. It's weird. So I'm not sure which one I want to try first. Do you want to? Let's try ratio test first. Can you guys set up the ratio test for this? Let's see if it works. Because again, it's possible it'll be 1. We'll have to see when we get there. Ratio and root test are really powerful. Root test we don't barely ever use because it's very rare that everything's to the nth power. The ratio test kicks so much ass. Let me catch up to you guys. 3n plus 1 to the fourth over 4 to the n plus 1 times the reciprocal. What's this limit here? 1. Is everybody cool with that? 'Cause, you know, so you just pick out the parts. And of course, what happens here? How many 4s cancel?
4 to the n.
Yeah,
cancels,
n of them
and
cancel.
then
So you
there's
get.
4 left over.
So what's this?
4. So it's 1 over 4.
Which is,
Less than 1.
which means
Absolutely convergent.
absolutely convergent. Kick ass. By the way, what I want you to realize, so we could do it the way I had you do this one, but ratio test, if it came out to be 1, then I would go back and do something like that. That would still work, obviously, but that's a shit ton easier, right? So when ratio test works, there's light coming off of it. You're like, oh, thank you. You know, the ratio test is just so beautiful. Okay, which might explain to you why I don't put 11.6 on the first test about this, because I don't want you to have it yet. Because I got to make you do weird shit. Yay! Okay, sorry. Okay. So real quick, what this means? In fact, what's R for this? If the top was 1 to the n, what is R for that? 1/4. So this grows so quickly that even when n is like 18 trillion, this is sort of, it means nothing next to 4 to the 18 trillion. So you're effectively multiplied by 1/4 because the top is changing by so little, it's comparatively like multiplying by 1. Does that make any sense?
Yeah.
Okay, maybe, okay. Maybe, okay. Okay, so let's pick another one. Let me see. Yes.
Can we do the integral test for this one? Because it's increasing, right?
Now here's the, well, let's see. If you wanted to. Do you want to? So one, you have to show, you have to prove all the requirements are met, right? So you have to show, and it's not that bad to show that that's decreasing. But when you set up the actual integral, so we'll say this, I mean, integral test is always there, right? what would you have to do to, what is that, 1? Yeah. How would you do this integral? Why did I put it so close? What method would you pretty much have to use? And I'm not saying we're going to do it. I'm not saying you should. But integral test is one of the tests you can always try. It's always there, right?
Yeah.
How would you try to do that integral? By parts. That's how I would try. Does anyone want to? No. But, all right, let me show you this. Is everybody cool with that? I want you to realize there's nothing keeping me from trying integral test any damn time I want to, as long as the conditions are met, right? Except for if this is really, should it? Okay. So for example, well, that's not the greatest example. Let me see. Well, let's take a look at this one. That's not exactly integral test, but this is just the next one I was going to do. What was it? Okay, yeah. This one's a little silly, but this is kind of funny. Would you want to do, well, all right, let me not lead you in any direction. What would you like to, can somebody tell me real quick, rattle off a few tests? So obviously the last two we did a ratio and root. We just talked about integral. What other things can I do? Say again? Alternating series. Limit comparison, I think is what you're going for?
Yeah.
Keep going. What other kind of comparison? Direct comparison, cool. And then you got, like the p-series and the geometric, right? Those are in there, correct? I think we got all of them. Okay. So, anybody have a suggestion on what test to do here? You can do it, you can do it.
Maybe a power series?
Say again?
Maybe a power series?
Oh, we're not quite, do you mean p-series?
I mean, P series.
Okay, because power series is an entirely different thing. We're not even, the next section is power series. P-series.
Yeah.
This is trying to be what? And I love the fact that some of you guys are trying to be doing that. Trying to be,
What's the power by
the square root of k squared is
now? Oh, it's just
k times k.
squared.
So it's trying to be 1 over k squared, which is, does everybody see what just happened? When k gets really, in fact, this right here is not work, it's just feeling the thing out. So you can do whatever the shit you want to. Kill the one, I don't care about that stupid one. So when k gets big, the one doesn't mean shit. So what is this trying to be? 1 over k squared, because that's what I get when I just kill the 1. So that converges, therefore, if I wanted to do direct comparison, I want a ceiling. So I want something that is bigger than this, and the easiest way to make a bigger thing here is to make the bottom smaller. And then I can't kill the one, right? Do you guys follow? And I still don't know if you guys are really cool with the fact that I could basically do whatever I want to make this inequality true, but there's a ton, how many things are bigger than this for all values of k? There's a ton. Is this true? Is this statement true? Shit, yeah, right? Is it useful? No, because what does this do? Diverges. So there's a ton of stuff that's bigger, and most of them diverge, correct? So this is why if you're not careful with what you do, you might go too far. You might make something that diverges when you really wanted it to converge. So you could easily go too far. There's a ton of shit that's bigger than him, and most of those diverge. So you got to be careful. So all I need is something that I know is greater than this always, that converges. So if I take that away, that does make it bigger, right? And if taking it away didn't make it bigger, what would I do instead? You do it. So I make it k squared plus k squared. Because k squared is bigger than 1 for all k greater than 1, correct?
Right.
So that would make the inequality go the right direction. Okay, in that case. Okay, so let's see, 1 over k times square root of k squared, which is 1 over k times k, which is 1 over k squared, which converges, blah, 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 right? Now, I don't know how many of you guys would think that given all the options we have, you would have chosen direct comparison, because most of the time direct comparison is one of the ones that people don't like as much. But do you see how there are problems where direct comparison is pretty damn easy? It is the thing to do, right? Okay. Let's see, what about, what you got, Jeff? There's something I have kind of neglected to say because, and this is hard for a teacher because I didn't create one, but as a student, see if you guys remember this. I need to make a big deal of this. What's the very first thing you try? Any freaking series I give you, what's the very first thing you look at? The limit test, right? The test for divergence, right? So I kind of gave this away. What's the limit of this as n goes to infinity? What's the limit of this piece? As n goes to infinity.
Oh, yeah.
Freaking 0, right?
So it's 1.
Yeah, so the limit of the whole thing is 1. So does this series converge? Nope, because that is not 0. Now, please do write that, because otherwise I'm not sure if you think that 1 means it diverges, right? It's the fact that it's not equal to 0, right? So don't forget that. It so sucks when you get some problem like that and you start doing all this weird shit, you start doing direct comparison, and you should have just did a limit, and you could have seen, bam, I got no work to do. The limit's not 0. So I really need to make a bigger point out of that. It's the very first thing you should try for anything is, if the limit's not 0, you're done, right? Okay. All right, let's see. Let's try one more. That was nifty. Yeah. Let's see if you guys listen to what the hell I just said. What do you try first? What do you look at first? Limit, right? By the way, so can you see that this is not immediately obvious what this is doing? Can everybody see that this is not like oscillatory to infinity? I mean, what is this approaching as n gets really, really big? This is approaching 0, and sine of 0 is 0. And what's this doing? Going to infinity. What's true about infinity times 0?
Oh, 0. Times 0 is 0.
Say again?
Anything times 0 is 0.
But anything times infinity is infinity, so.
Black hole.
Indeterminate. This is an indeterminate form. By the way, real quick, there's nothing wrong with you using anything times 0 is 0. I totally agree with you. Is this ever 0? Does it ever equal 0? No. Right? Because does this ever get to 0? So sine of 1 over, my favorite number, 18 trillion, is not 0, correct? It never is 0. I really want you guys to understand this. So that's why something like infinity minus infinity, do you guys remember that's indeterminate?
Yeah.
On the surface you think it's 0, but it totally depends which one is going to infinity faster, right? That's the whole point. So which one? Is this going to infinity faster, in which case the answer is infinity? Is this one going to 0 faster, in which case it's 0? Or are they both going to the stuff at the same rate, in which case the answer is like 2? I don't know. So how the shit do I do this? How the shit do I do that shit, Jeff? Yeah, don't make a joke out of it, Jeff. Tell me. I'm sorry. I'm getting all meta. I'm sorry. I'm sorry. Anybody remember how the hell to do this? Can you? It's indeterminate form, correct? Is it the right indeterminate form to use our favorite medical person?
No.
Why not? What's it required? What's required to use? Has to be a ratio. You guys remember what to do. This is not currently a ratio. Can you make it? You can make any damn thing a ratio you want to, correct?
Yeah.
How do you make 7 into a ratio? 7 over 1, but be even better than that. 1 over 1/7, right? There's a ratio, right? So how to make n a ratio? How do I change it?
Sign all that over 1 over 1.
Yes, so those are equivalent, right? Now can you apply L'Hopital's? Well, what form is it in now? This is going to 0. This is going to 0, right? Indeterminate still. Of course it's still indeterminate. So then I apply so what's the root of sine of something? Cosine of that thing. And then the thing gets a turn, right? Basically every derivative rule is everything gets a turn. Yes? So what's the root of 1 over n? Negative 1 over n squared. And what's the derivative of 1 over n? Oh, that kicks so much ass. Die, right? So as n goes to infinity, what does this go to? 0. And what's the cosine of 0? 1. What does that mean? What does that mean? Which thing were we just doing? Were we applying
Diverges.
the test for divergence, right? So since these elements go to 1, this is divergence, not 0. You guys kind of with me? Now, real quick, as a student, one thing that happens is you start doing a limit and then you forget that you're not doing a ratio test or something, right? Or you're not doing, like, if you got 1 there, you might go, oh, this is inconclusive. No. The limit of the freaking elements isn't 0. It diverges, you're done, right? Okay, maybe. That was not obvious at all. You guys agree with me? Now, to be really honest, how many of you guys remember this fact here? Well, it's going to 0, but yeah, let me see. How many of you guys remember this? Remember that from Calc 1, anybody? No, okay, so it's okay. It depends on your Calc 1 teacher if they made a big deal out of this or not. But that was something from Calc 1. Now watch, you ready? Watch this. So if I do this, that would mean that now I'm letting x go to infinity, which is basically what we had here, isn't it? Okay. That's all side note. That's all a side note. Just a little thing about the more you know, the less you have to do. It's one of my favorite sayings. Okay. So 11.7. If I were you and I was about to do section 11.7 homework, I would have that sheet that I gave you a while back with all the different forms just sitting next to me. And just reference it, right? Now, as you do that, you do want to try to test yourself and see, can I determine something without looking at my notes or something? But still, you got that sitting next to you, so you can kind of refer to that as you do that homework. Okay. All right, so last thing for tonight, because we're going to get out of here a little early. I want to kind of lay the groundwork for section 11.8. So 11.6 was ratio root test. 11.7 was every test all at once. And now we're going to get into 11.8. 11.8, by the way, has anyone noticed my shirt? Have you ever seen this before?
Yeah.
So real quick, this says that e to the I pi, wow, Jeff, plus 1 equals 0. Math people freak out about this. I walk by a math person with a shirt like, oh yeah, I'll show you. Because e, isn't that a special number? Pi, isn't that a special number? I, isn't that a special number? 1 is the multiplicative identity. 0 is the additive identity, right? There are 5 freaking fundamental numbers involved in this silly equation. And then the equation itself, some of you guys, is anybody looking at how the shit does that work? What the shit is e to the I? What the hell are you talking about? So we are going to learn over the course of the next 3 sections, you are going to be able to prove this. You are going to be able to see why this is true. Is anyone intrigued?
Yeah.
Okay. It's one of the coolest things ever. So that is coming, which is why I wore this shirt. A little advertisement. Okay, sorry. Okay. That's Euler's identity. Euler did too much. He didn't leave anything for anybody else. It was like, come on. Him and Gauss did too much. All right, so what we're getting to, 11.8 is called, the idea we're talking about is power series. And what a power series is, it is anything that is in this form. Now, real quick, if n is, in fact, let me make sure one thing. Let me make sure about notation from this book. Okay, this is the one, that's right. This is the one place I agree with him. Okay. Change this to 0 real quick. This is one time we're going to actually start at 0. Can anybody tell me, like, if n is 0, by the way, real quick, this here is a constant, but it's a function of n. So it's a constant, like, for each element, it's a constant, correct? The only variable in here is x. That's what we can figure out. This is some given function of n. So let me give you an example. Here's an example of a power series. There's a power series. What's Cn? N over n plus 1. So for n equals 3, what is that? 3 over 4. So it's just a constant. For every element, it's a constant. If n equals 3, this would be x minus 1 cubed, correct? Can you start to see, for n equals 0, isn't this part not there? 0 power? Then it's a first, second, third. So what is this really? This is an infinitely long what? You could do it, you could do it. X to the 0 plus stuff x to the first plus stuff x squared plus stuff x cubed. What is that? Polynomial. It's an infinitely long polynomial. You guys see that? N is just going up, written in ascending order, right? So it'd be like 1 plus x squared plus x cubed plus x to the 4th, right? So if I made another example, is that a power series? Power. What can I actually, okay. Is that a power series? What's Cn? You can do it. What's Cn? 1. Beautiful. It's just 1. It's always 1. What's A? 0. Beautiful. So is that a power series? Shit, yes. What would the term, I'm sorry, I keep putting 1. I'm so used to putting 1, and you will be too, I'm sorry. It's just the way it goes. First element would be 1. Second element would be x. Right? N equals 0. N equals 1 is the second element. N equals 2. Wait a second. N equals 0. N equals 1. N equals 2. Yeah, okay, beautiful. And so forth. Blah, 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 blah. Real quick. Just a little side note. What kind of series is that? And you can tell from right here. What kind of series is that? You can do it. Geometric, where the base is not determined yet. So okay, so let me focus on this. Let me make some general statements, and then we'll call it a night. So we're almost there. Okay, so this is what the power series looks like in general. It could be any function of n, has to be defined on this, of course, in front of x minus any constant to the n. So it's just any general, basic, infinitely long polynomial. You know, your run-of-the-mill, infinitely long polynomial. So look at this guy. if x is 1/5, can anybody tell me anything very specific about the resultant series? I keep putting 1. I'm just going to keep doing it. It's convergent geometric series, right? What if x equals -11/10? Divergent, because the absolute value of that is bigger than 1, so that's the divergent geometric series, right? So no matter what the hell x is some kind of geometric series. Can somebody please tell me what's got to be true about x? Oops. Has to be less than 1. Greater than -1, right? Now, real quick, okay, here's the last thing we're going to do. Does everybody see that? Does everybody come on? That's almost a silly thing. I'm like, let me make a geometric. What can I put in there? Anything I want to. So that's all I'm saying here. So then I'm saying, if I wanted to converge, I better make it between -1 and 1, right? Can you please, last thing we'll do today. I think I've said that a few times, so do that. Let's apply the ratio test to this thing. How do I do that? What's the next term? So the nth term is x to the n, correct? What's the next term? X to the n plus 1. What does that equal? How many x's cancel? Yeah. So n x's cancel, so you get that 1x left. And that's this, correct? Now, real quick, we just applied ratio test, correct? What's got to be true about the result for it to be convergent? Has to be less than 1. And what is the absolute value of x less than 1? Right? It matches with what we knew was going to be true. Now, why were we able to figure this out without doing this work? Because that's freaking simple. So what's going to happen to us? We're going to have some Cn that's not just 1. Maybe it's n over n plus 1, right? We're going to have other shit happening. So I'm going to do the ratio test. It's not always going to be 1 and -1. Okay, what about if x is 1? Because remember, what's true, if it's equal to 1, what's that mean? Inconclusive. So I have to check. If x is 1, the ratio test doesn't have a clue. But can anyone tell me if x is 1, what's going to happen? Yeah, add 1 forever. That's divergent, right? What if x is -1? Yeah, now it's -1 to the n, so it's divergent for sort of a different reason. It's oscillating between, right, 1 and 0, 1 and 0. Yes? So we call this the interval of convergence. It's sort of like the domain. Domain means the inputs that doesn't make the function freak out. So aren't these the inputs for x that doesn't make the series freak out, diverge? So the interval of convergence is sort of like the same idea as domain, just on a different kind of level. Yeah, let me give you this, and that'll be enough. So there's a handout for 11.8 and 11.10. I'll give this to you in case you want to glance at it, but bring this back with you next time, and we'll do some of this stuff. Then, otherwise, we are done. Thank you. Anytime. Oh, yeah.